the Atal Faculty Development Program on AI integrated next generation semiconductor devices. I hope you are all doing well. Yesterday was an incredible day filled with insightful sessions from our distinguished resource persons. We were very fortunate to have experts from both academia and industry who shared their knowledge with us. Their presentations not only enlightened us but also gave us a glimpse into the future of artificial intelligence and its transformative impact on next generation semiconductor devices. Once again, I would like to extend our heartfelt gratitude to our resource persons for sharing their valuable time and expertise with us. Now it's my pleasure to invite Dr. K. Kiran Kumar Rao, our co-coordinator of this FDP, to introduce our first session's resource person, Mr. Surjit Bhattacharjee. Dr. Rao, please take the stage and introduce our esteemed speaker.
Good evening. I am delighted to have the opportunity to share the profile of today's exceptional resources person. Mr. Surjit Bhattacharjee is a distinguished senior lead engineer in research and development at Qualcomm India and Qualcomm Inc., San Diego, USA, bringing a wealth of expertise in advanced digital engineering and verification technologies. With a distinguished professional trajectory that includes significant tenure at industry giants like IBM and Intel, he has established himself as a specialist in complex technological domains. His technical expertise spans critical areas including neural signal processor design verification, video analytics and processing subsystems, compression and decompression engines, vector and matrix precisions, and the power and performance optimization. Currently pursuing his PhD at Birla Institute of Technology and Sciences, Pilani. His doctoral research focuses on AI-driven advanced functional verification of digital IPS, complementing his already robust academic credentials. Bhattacharjee holds a master's degree in digital electronics and advanced communication from Manipal Institute of Technology, MAHE Manipal, and has established a strong academic research profile with multiple publications in prestigious international journals. His multidisciplinary background and continuous prestigious of cutting-edge technological knowledge position him as a significant contributor to the evolving landscape of digital engineering and processor design. I now invite Mr. Surjit Bhattacharjee to take the session forward and inspire us with their expertise. Thank you, sir. Welcome.
Thank you so much for the warm introduction and inviting me to take up the session. It's a privilege on my part as well to prepare and present before you. So thank you so much for the opportunity. Without wasting much of time, now we'll move on to the presentations because I have a lot of things to cover and I would expect the session to be as interactive as possible. Please feel free to stop me at any point of time. If you have any questions, we can answer that right then. But I would prefer the questions to be brief and the answers will be brief so that we can cover a lot of things in the sessions, right? So having said that, we'll get started with the session and I'm sharing my screen. Please let me know once you're able to see. So I might have to annotate certain things because we'll be doing some maths also in this session and not very complicated mathematics, of course, but simple things to get things clear. So this is the topic of discussion today, power management and energy efficient semiconductor design. So first question is, why do we need power management? We'll answer that question in the third slide of this presentation. Why do we need power management and why are performance-centric devices so power-hungry? Because there are a lot of heavy-duty graphics, a lot of heavy-duty CPU cores coming up, which are serving millions and billions of server calls. There are banking sectors and other crucial, critical, mission-critical systems working on a lot of projects and a lot of chipsets are involved there. So it's a lot of it's consuming a lot of power. So we want to mitigate that, and I'll tell why this is so essential. So we'll get started. So the contents of presentation would go something like this. We'll talk about the overview of ASIC design flow. That's the reason I wanted to know the pulse of the audience, and I got to know that it's a multidisciplinary audience. So it'll be better if I just briefly go through the ASIC design flow. Then we'll talk about Moore's law, which is definitely the dictionary for us, the VLSI engineers, and power specific interpretation of that. That means what Moore's law actually means in terms of power. That we'll understand. Secondly, we'll talk about the need for low power VLSI design. As I was mentioning, we'll cover that in the third slide. And then we'll talk about the functional intent versus power intent. Why do we need power oriented design? I mean, power centric design. And why non-PA, I mean, non-power aware simulations don't usually help in catching issues or bugs at the pre-silicon and post-silicon level in the fabrication. And power saving strategies. These are the basics, very basic strategies that we must know. Then we'll talk about UPF. UPF is Unified Power Format. It is IEEE standard methodology, which is used across the industry. Everywhere you go, it is the UPF, which is basically used for the power insertion and also the power aware verification. And then we'll talk about the components of UPF. Some of them you might have already heard. Some of them you'll be hearing for the first time. We'll talk about them. And it's not a very rocket science. It's a simple thing. And towards the end, we have an interesting topic to discuss, understanding the UPF implementation. There I'll take up a real design module, and I'll show how UPF is actually implemented in industry. So UPF is a format basically which is used to, insert the power domains, power rails, power nets, power ports, and we can, dynamically switch on or switch off the power based on the requirement of the IP. We'll go towards that, but initially we'll talk about what are low power serial peripherals do we see around us. Say, for example, right now some of you have joined through laptops, right? In laptop, you might have seen a touch sensor, right? A touchpad. So the touchpad is basically, the response is basically received by one I3C controller. I3C is not listed here. That's improved inter-integrated circuit protocol. That's one of the low power, low speed serial peripherals. It's a 2-wire protocol. When I say 2-wire, it's a data line and a clock line. Okay. And now this peripheral only needs attention of the CPU when somebody touches it, right? If the touchpad is not at all touched by the user, do you need always the power to be provided there? Otherwise, you'll be investing a lot of power, right? Power will be wasted in that way. Similar way, your laptop has got a camera. When you turn on the video, then only the camera needs to be powered on. Otherwise, the camera does not actually require a power, right? For the efficient power management. So these were the areas where we understood that there can be certain sensors, certain integrated sensor hub around the SoC system on chip, which can be powered down, power gated based on the requirements. And then we understood that we need to handle the power management efficiently. There should be a system within the SoC, say you can name it as power management and control unit, that would efficiently control the distribution of power to the specific segments of the SoC. One of those segments can be I3C, which I was talking about, which will be able to, control the touchpad, touch sensor. Then we have HIDs, human interface detect, by I2C sensors. Then our Wi-Fi is on SDIO. Whichever application you see here is like the auxiliary action of the system. It is not essential action of the system. So your CPU does not need to supply power to all these things all the time. If you're not supposed to take a meeting from your laptop, you might not require a Wi-Fi to be connected always, right? To work. So all these things are customizable, programmable, and can be, efficiently managed using a power management and control unit. Now, today's topic is basically how to code a low power design, how to efficiently handle and manage power. So gradually we'll move towards that. So before that, as I mentioned, we'll cover the overview of ASIC design flow. Now, full form of ASIC we more or less know, which is application specific IC, integrated circuits. Now, the first step that you see here, the first step is specification, right? So this specification comes from a market survey. So today, Intel's chipsets are competing with AMD's chipsets. Every day, there are people who are investing good amount of time in doing a market survey and market research, in understanding what is the customer's need, what is the end user's requirement, and bringing that to the architect. Based on the specification, there is architectural design coming up. Now, from that architectural design, there are two views basically. One, understanding the architectural design, a design engineer will code the RTL. Okay. And understanding the architectural design, the RTL verification engineers will code the verification environment. Now, verification is so crucial. Let me tell you a story. I guess I don't recall the year, but Intel had a Pentium 4 bug, and any bug, it was a floating point bug. So it was not able to calculate properly, I guess, fourth decimal or fifth decimal place in a division. So it was an error by a system clock. And you know what Intel had to do? It had to call for a respin. And when a respin happens, it's a huge loss on a company. Name, fame, and brand value of the company goes away. So it was a very difficult situation. It was a very tough call. So Intel had seen those days in the past when Intel Pentium 4 bug was always, was all over the news, and they were all talking about it, that hey, we have missed a bug. So it's very difficult. So RTL verification engineers should do their interpretation of the design, like what the design should actually do. That should be tallied against the RTL design. Now, next step of that is the design, when it is verified at the pre-silicon level, will now go to synthesis stage. What is synthesis? From RTL design, we prepare the net list, right? So synthesis is a stage which basically prepares a net list out of RTL, right? Then we have gate level simulations. Now, those nets will be further brought down to gate level simulations. Now, gate GLS is basically a long time consuming mechanism, and we don't do with zero delay. Zero delay is the functional simulation. Now, gate level simulation is we add some delays. Now, why delays? Because when we fabricate the device, there can be a lot of interstitial delays in the path. There can be metal delays, there can be WAD delays, there can be clock to queue delays, right? When we do RTL simulations, we don't consider all such delays. There can be a lot of delays. And because of those delays, there can be metastable stages. Okay, there can be metastabilities, right? So that's the reason we do a lot of gate level simulations. We do on a standard delay factors also, which is SDF, then PD, which is basically post floor plan, and post netlist, basically post netlist design. Now, nextly, we do what we do design for test. Now, design for test is a methodology which is very famously known as DFT. There are various segments of it, DFD and others. There we test the scan interface, the debug interface, JTAG debug interface. What happens when your system encounters a fault? You basically cannot see the waveforms and you can't start debugging because your now chipset is fabricated, or rather, you have only few debug ports through which you can, verify what is the issue in the system. So you need some debug ports and some debug signals to be traveled. So that is done through the design for test interface. When everything is done, we move ahead and we do floor plan. Floor plan is again a backend flow for floor plan placement, CTS, which is clock tree synthesis. We find out whether there is a multi-cycle path or false path in a design. Then we do routing, right? We do efficient wire management through the routing. And then finally, we do a post-silicon validation by running some tests and then sign off, and we send it to fab. And finally, post-silicon validation happens on the chipset, right? And finally, we get the chip manufactured out in a complete process. So this is how it happens. So far, we have just covered the overview. Do you have any questions? I'll just take a moment here to hear from you if you have any questions so far. Otherwise, we'll move on. Now, who doesn't know Moore's law? Now, I proudly tell that I belonged to a company once, and that was my first company, which was founded by, or rather pioneered by Moore's law, right, which was Intel. And this slide deck which I've taken is from Intel. So Moore's law says, I will take a take a pen and try to explain certain things here quickly. So Moore's law says in every 18 months, the transistor size is supposed to be doubled, right? So sorry, the transistor counts are supposed to be doubled. My bad. Now, what does it actually mean? That means that if you have, say, a chip area as what I'm drawing right now, hope that is visible. So, okay. So now assume this chip has a length L and breadth B, right? So what is the area of the chip? L into B, right? This is the area of the chip. And in this area of the chip, n number of transistors can be accumulated, can be accommodated. Now it's saying after 18 months, the transistor count will be 2n, right? Now we are saying in the same area, 2n number of transistors can be accommodated. What does it mean? That means the effective length and breadth of the chipset will become half. Sorry, rather 1 by root 2 times, right? 1 by root 2 times, in which we can fit in n number of n number of transistors. So to fit n number of transistors, we don't need the whole area of the chip. We need only half the area of the chip. As a result, we are seeing the gate length of the chip is actually decreasing, right? This is showing a reducing gate length, which is L by root 2. Now, what are the consequences of this? When we have reducing gate length, the capacitance of the transistors go on increasing. We know the gate length, the relation of the gate length and capacitance, it's a parallel plate capacitor. And the gate length is, if you consider the gate length as L or D, it's epsilon naught OX, which is the oxide permittance into A, area of the chip, rather area of the parallel plate divided by D, right? D is the distance between them. Now distance is becoming 1 by root 2 times. That means capacitance is increasing by root 2 times, which is 1.414 times. Gradually, the capacitance of each transistor is increasing. What does it lead to? Right? What does it lead to? Let's see. What is the formula for dynamic power dissipation by a transistor? It is proportional to CV square F, where C is the capacitance of the transistor, V is the applied voltage, and F is the frequency of operation. Now, if C keeps on increasing, you see the dynamic power keeps on increasing. There's also one more factor. If you just remove the proportionality sign, there's a proportionality constant, which is alpha. Now, this alpha is a switching efficiency. So, more the number of transistors, the switching activity of the transistors will keep on increasing. The alpha will keep on increasing. So earlier you had n number of transistors. If the collective switching activity is alpha, now you have 2n number of transistors, you have 2 alpha times of switching activity, right? So your alpha is increasing, switching activity is increasing, capacitance is increasing. Overall, your dynamic power dissipation is increasing by a few folds. Now we understand why it is so critical. By increasing more and more number of transistors over every 18 months will no doubt improve a lot of performance, because now lot of transistors will be involved in giving you the best graphics, giving you the best speed, will give you the best internet, because there'll be network chips, good network chips. You will get the best performances. But what is the trade-off? Trade-off is the dynamic power dissipation, right? While saying that dynamic power dissipation, there are also certain things like static power dissipation. Now, what is static power dissipation? So, static power dissipation is closely associated to the leakage current. So, if your circuit, as I was telling, right, there are certain things which are not required. For example, currently we are all on, off video mode. We don't require a video, right, for the discussion, for the presentation to happen. Now, my video is shut down. Imagine if the moment you join the Zoom call, the video is turned on. What happens? Even if it's required or not required, there's a constant power supply to the video, right? And what happens then? There's always a leakage current associated, and that leakage current will lead to a static power drop, power dissipation, right? So there are two types of power losses that we have spoken about. We'll move on to the next slide. So now that we have understood how many types and how many patterns of power losses are there and why the complicated designs are so power hungry, we'll look at a design and try to understand three major factors, like how the implementation is. So in this, I have taken an example of a simple SoC which has got a CPU core, which has got an internal memory and then external bus, then a lot of low power peripherals. If you see GPIO, SPI, serial peripheral interface, and then you have I2C timer, RTC clock, right? A lot of modules are there which are independently working, but they are connected to a common supply bus. Now, what happens? Consider that the CPU core operates on a frequency of 3 gigahertz. Okay, so this is the frequency rating. Pardon for my writing, it's not coming proper, but hope you are understanding. Assume that the CPU core's operating frequency is 3 gigahertz, and assume that the GPIO, right? GPIO's operating frequency is 2 gigahertz, right? Operating frequency is 2 gigahertz. Now, okay. So now this operating frequency is guaranteed when you have a supply voltage. There is a requirement of supply voltage also. It's saying that the voltage rating for this operation of 3 gigahertz of CPU core is only when you provide a supply of 0.1 to 1.6 volts. And for the GPIO, the rating is 0.6 to 1.2 volt. Like how we get bulbs from the market, right? And bulbs are given a power rating and also frequency, not frequency rating, of course, the voltage rating, right? That it works in this voltage, it has this wattage. Similarly, different modules have different ratings. Its operating frequency is 3 gigahertz, which can only be achieved when you have a supply voltage of 0.8 volt to 1.6 volt. You can provide any voltage of your convenience in this range, 0.8 to 1.6. For the GPIO to work better in 2 gigahertz, you require to supply a voltage of 0.6 to 1.2 volt. Now you tell me, if you have a common supply net, any one of you can try this. If you have a common supply voltage, what voltage would you like to have? What voltage value? It's a very, very easy question. Probably you can give it a thought. What one single voltage which can apply to both the modules so that they can work efficiently? Any answer from the audience? Am I clear with the question? Okay. So, if I would have been a layman, I would have taken a voltage of 0.8 volt to supply to both. If I supply 0.8 volt, this no doubt will work with 3 gigahertz, and this will no doubt work because it requires 0.6 to 1.2 volt. It will generate 2 gigahertz frequency and it will work absolutely fine. There'll be no problem at all. Now, what am I losing? I'm giving additional 0.2 volt supply to GPIO, which is not at all required, which is going as a total waste. Now, what is the level of wastage? You don't look at 0.2 volt. You imagine 0.2 volt square, right? And how many such transistors do you have involved in that? So all the transistors in the same power domain. So you're basically feeding the same voltage to everyone, right? Inside the GPIO. Because it is basically depending on the square of the voltage. We've already seen the PD is CV square F, right? Alpha CV square F is proportional to the square of the voltage. So you're wasting 0.2 volt square of the amount, and then those many number of transistors if you have, you're losing that power, which is not efficient. Okay. Second thought which can come is, can I not give one single power rail to this CPU core and another power rail to GPIO? Yes, of course, you can give 0.8 volt. You can give 0.8 volt supply to this CPU core and 0.6 volt supply to this GPIO. Is there any problem now? When both are efficient? Anyone from analog background can answer this? Will there be any problem with respect to this kind of setup? Okay. So, yeah, there'll be issues with respect to noise margin. And of course, we will require our level shifter because this is at a different operating voltage and this is at a different operating voltage. The signals which cross the domains, right, from GPIO to CPU core, there'll be signals which are interacting, right? Those signals will suffer a noise margin loss. I'll talk about noise margin loss in the next slide. And imagine the third condition, when you don't require the GPIO, what is going to happen? When we don't require a GPIO, the signals coming out of GPIO are all X, all unprecedented, cannot be found out. Like what are the values of these? And these are being connected to the CPU core. So eventually it will corrupt CPU core signals as well. Right? And this is called X bleed or X propagation in industry. Right? If you don't efficiently manage power of both the domains and you have signals crossing one domain to the other and it's floating X, it will cause X propagation, which is briefly called X prop or X bleed. Okay, that will corrupt the other logic also. Right. Now, having said that, we'll move on to the next topic because these are the three major challenges we figured out, at least from a simpler design perspective, right? See, thinking about low power is not only going to help, not we have to think about a solution which is convenient and which is scalable, which can be applied across all the designs. Right? Now, let's look at the differences between the functional intent uh, and power intent. Like what do they specify? But when I share the slide, I would request you to go through. I would like to talk about this slide, rather draw something and show you what is actually a different thing in this functional intent and power intent. So let me draw a very complicated, very critical design for you. Oh, need to change the color. So this is the most complicated design I know in VLSI, right? Design, right? So what is this? This is the most complicated design, right? What is this? This is a NOT gate, right? I was just kidding. Right? So this is the expression. So what I've written just now is a behavioral modeling of the NOT gate, right? So this is the NOT gate. If the input is A, the output is X. X is equal to NOT of A. Now assume you have an AND gate also, where you have an input as X and B, output as C. So we can write down C is equal to X and B, right? Now, what are we missing here? Let me draw one CMOS inverter. That will clarify the case. What am I missing here? It's been years now. I am drawing CMOS. I have not drawn for a long time. Please pardon me or correct me if I am making any mistake. Hope this is correct, right? So Vin is the supply input and we have a PMOS here, we have an NMOS here, and we take the output from here, right? Now, what are we not missing or what are we missing here? When we provide an input as 1, this is short circuited. The NMOS is short circuited, right? When it is short circuited, the voltage from ground will propagate and will appear here at Vout, which will become 0. When I provide value 0, this NMOS is open circuited and PMOS is short circuited, and the VDD will float down to Vout and its value will be 1, logic 1, right? So this is how a CMOS inverter works, right? We forgot a basic thing or we missed a basic thing here. What if the supply ports are not properly connected? What if the designer has made some blunder mistake in connecting supply ports properly? Like if VDD is not tied off to the voltage rail itself, because it's a design, right? It's a hand-coded design. People may make mistakes, may not bring it up to the power ports level. The port may be masked, or there can be multiple other operations. There can be voltage domain crossing from one domain to the another domain. They forgot to tie off certain signals, and that's the reason the voltage is not coming up. So in the RTL behavioral simulation, we never consider the consequence of the VDD and VSS, the voltage supplies. If we don't consider, we are missing a lot of scenarios. Suppose if this voltage is not connected, if this voltage is X, which is unprecedented, what are we going to see? No matter what we provide here in the input, 0 or 1, what are we going to see here? We are going to see always X, right? Because the complement of this logic which is coming down, floating down till here is X. So it'll give you X always, right? So this is the difference between the normal RTL simulation and the power aware simulation, where we also not only consider the behavioral model of the RTL, but also consider the power ports, whether the power is properly connected or not, right? So the right equation for UPF based, when we say power aware design verification, the right equation would have been this: X is equal to naught of A if and only if VDD is equal to, say, 1.5 volt or 5 volt or whatever is your logic high, and VSS is 0 or minus 5 volt or whatever is your negative voltage or ground, right? Whichever, right? That could be a proper condition. Now, who will bring this condition? In RTL simulation, the term itself is called simulate. So we simulate as if there is a voltage, but there is no physical voltage available. Then how can we catch hold of these issues? Then we came up with something which is called UPF, right? Before moving on to that, I would like to talk about the power strategies. But even before going to power strategies, I would like to take one more moment to complete this part, because the remaining part will be very easy to understand if you understand the requirement. Now, why do we talk about all such things? Now, a few moments back, I was talking about noise margin, right? Why noise margin plays a critical role, we'll look at it now. So let's assume we have a design as this. Let me rub it. Okay, and followed by a NOT gate. Okay, now the same thing. Suppose the inputs are A and B, and output of A and B is C, and output of C is D, right? But now here we have two different voltage supplies. One is V1, other one is V2. Okay, first one is V1, other one is V2. Now, why two different voltage supplies? Because they may belong to two different voltage domain. One may want to switch off this while turning on voltage 2, right? So we have two different domains. Now, the noise margin for V1, say for example, is such that V1 will be considered as 1, which is logic high, if the voltage is greater than 0.4 volt, or it will be considered as 0 if the voltage is less than 0.3 volt. This is the noise margin definition. Okay. If the voltage level is more than 0.4 volt, it will be considered as logic 1. And for this, it will be considered as logic 0. For V2, we can have a different requirement because these are two different voltages from two different domains. So we'll say it is 1 when it is more than 0.25 volt. And it is 0 when it is less than 0.2 volt. Hope it is clear. Now, what we are saying is, if the voltage level is more than 0.4 volt, we'll consider that as logic 1. If it's less than 0.3 volt, we'll consider that logic 0 for voltage V1. Now, when we see the C is having a value 0, suppose C's value is 0 for any combination of the AND inputs, say either A is 0 or B is 0 or whatever be the reason, right? C is equal to 0. Now, this might correspond to a voltage level of 0.26, because 0.26 is less than 3 volt. At the V1 perspective, it is having value 0, which is justified. Now, this C enters into another voltage domain, which will consider it as voltage 1. See, anything greater than 0.25 will be treated as 1. So you will see a 0 here, and at the output of the NOT gate, you will again see a 0. Because when it enters the input of the NOT gate, it will consider that input as 1. Because the voltage value is 0.26, which certainly qualifies the first case. If we consider the noise margin for the first case, it considers, because its value is less than 0.3 volt, which is 0, which is rightly correct in this scenario. When it goes to the second voltage domain suddenly considers it as 1, right? Which is not proper, which is illegal basically. So you will see 0 at both the ends, and you will see some mistakes here. So in order to overcome such situations, we consider a special technique called level shifters. Now, if you are analog engineer, you must be curious to know what is a level shifter. Level shifter is nothing but the clipping and clamping operation. Okay, but it's not done through a diode, rather it's used through amplifiers and attenuators, right? In the digital design. Now, if your voltage level is down, bring it up to the next voltage level. So it's basically a voltage scaling. Okay, so that is required. Otherwise, what will happen? One value in one voltage domain will not be comprehended correctly in the next voltage domain, and it might clash, give some errors. There can be one more expression. Say, for example, suppose V1 is a function of V2. V1 is a function of V2. How is that possible? V1 is a function of V2. Say, for example, you have an AND gate which has an enable signal and V2. Now you see, if enable is equal to 1, V2 is equal to V1. If enable is equal to 0, V1 is 0, but V2 still exists, right? So V1 can be powered off, where V2 can be comfortably still used. Now what is going to happen? There is no specific input at this level, which is C, which is going undeterministic. If the V1 does not exist at all, if enable signal is equal to 0, V1 does not exist at all, the output of the AND gate is going to be undeterministic, which is going to be X. Now, that will corrupt the output of the NOT gate as well, even though there are two different voltage level. Then people thought of clamping this to a value and isolate this input to the NOT gate to some other signal. That strategy is called isolation. We'll talk about it when we go to isolation. But this is just a brief concept as why do we need what we are talking about, like whatever concepts we are talking about, why do we need them? We need to isolate signals because if we see a corruption at this level, because this V1 is shut down, we'll see a corruption at the next level also because it's a cascaded connection, right? We'll see the same X being propagated at the next clock cycle, at the next iteration that we don't want to see. Okay, so this is what I had to explain theoretically, and now we'll go back to the presentation again. So we have covered all these, right? Now we'll start with the power saving strategies. Now, what we have in power saving strategies, we have two efficient techniques called clock gating and power gating. The first thing is we do clock gating to avoid clock. If we don't pass the clock, there'll be no frequency. If there's no frequency, there'll be no switching. Frequency is off. So basically dynamic power dissipation is off. Always, if you want to comprehend such expressions, just remember the dynamic power dissipation's expression, right? Which is alpha CV square F. If there is no clock, there is no switching. If there's no switching, there's no dynamic power dissipation. So we can basically shut down an active circuit and make it inactive for the time being if we don't supply the clock. Okay? But if we don't supply the clock, but still supply the VDD, can anybody tell if there is any problem? I already spoke about it. Can someone, give an insight? Suppose if I block the clock, I don't allow the clock. For a moment, this circuit is not working. I will make the circuit inactive by not supplying clock. Can someone tell if there's any problem with the power dissipation if the voltage rails are still connected? Okay, there's still a problem, as I've already mentioned. There'll be still leakage power because there'll be leakage current. Leakage current will cost the static power loss that we don't want to avoid. in order to avoid that, we need power gating. We'll switch off the power supply also, right? Now, when I say power switch off, it is not like a switching off a fan or switching off a light. We actually don't apply always a switch. See, electronics implementation is little different. If I don't want current to flow through, I will make circuits equipotential. I will not provide a switch if I have to logically do it. So UPF, when it strategizes, it just knows that I will either make it equipotential or I will cut off the ground. If the circuit is not completed, there will be no current flow. So suppose, is there any requirement that you need to place the power switch here? You see a switch here. Instead of that, if you would have put a switch at the ground, it would have still worked because it will not complete the circuit, right? So the strategy may differ, but the concept will remain as is, right? We can apply a switch like thing using equipotential or applying a specific switch, power switch, through which we can also control the static power. Now, point is, when we say we can do clock gating, we can do power gating, what are we actually achieving? When we do clock gating, the IP is still accessible. You can access, you can read a register, you can do a lot of operations. But if you cut off the power, it becomes inaccessible. So there are two types of power gating. One is called accessible power gating. If you're doing clock gating, you're doing accessible power gating. You can still access the chip. If you do clock gating as well as power gating, you are basically making it inaccessible. You can't access it. Now, questions may arise. For a circuitry, if you are making it completely inaccessible, how will you recover? Because such scenarios will come, right? I will cut it off fully, cut off the power, cut off the clock. How will I recover the circuit? Now, there are a lot of reset mechanisms called hardware reset, software reset, reboot, right? There are a lot of mechanisms basically through which we can subsystem restart, through which we can recover the system. Okay, you might be already knowing these stuffs. Now, second thing is to work on the multi-voltage design. So basically, there can be different voltages. We have already spoken about it, and we've also talked about the problems, right, in the multi-voltage design. One was when the signals were crossing one domain to the other, you can have problems with the noise margin. We might require a level shifter for that. And the second thing is when signals crossing one domain to the other, if the one domain is switched off, it will have unprecedented signals, throwing into the next domain. That'll give a problem. Second thing is a good thing, is a very interesting thing, which is a frequency scaling. So voltage scaling is giving a lot of issues we have seen. The second is frequency scaling. Can someone please tell if there is any drawback of the frequency scaling? See, by scaling the frequency for some time being, you can actually reduce the speed. The frequency can be reduced, and CV square F is the equation for the dynamic power dissipation. Now, can any one of you please tell if there is any trade-off of the method, the frequency scaling? Okay, the performance will be compromised, right? So you don't want to connect a 1 terabyte hard disk, and you don't want the files to be transferred for 2-3 days, right? You want energy efficient application. Also, you want a minimum speed of operation. So all the interfaces are defined with a frequency band, and it needs to perform to its expected rating, right, which we call a claimed value that it should meet. Otherwise, there'll be a question on the benchmarking. Basically, say for example, we say I3C is max speed is 12.5 megahertz. We say I2C's max speed is 3.4 megahertz Mbps. That's the speed. How can we achieve such speeds if suddenly we do frequency scaling? Right? There'll be problems. Now we'll talk about UPF fundamentals. So what is UPF? UPF is Unified Power Format. It's a tool, it's a methodology this tool is basically a way of writing the power ports, power nets, supply nets, and it also governs a strategy as how you should have your, power management cells in the design. Now, when we say power management cell, it's an interesting idea. I would like to explain everything in brief, keeping the time in mind. But I would request everyone to go through the slides. I have a lot of information in this slide deck that will help you become self-sufficient UPF experts. And also you can start coding. I have some industry experiments and findings also included here, right? So it is used for power strategy implementation. Now, what is a power strategy? As a few moments before I was telling, right, that few moments back I was telling that I need to shut off the camera when somebody did not turn on the video in the Zoom call. I need to shut off the touchpad if I do not detect a touch in the touchpad. I need to shut off the keyboard backlight if there is no key press, right? There can be a lot of choices. Now, who has the choices? The choices belong to the architect who is designing it. That how he wants to design. Based on that, who will do the implementation of the power strategy? The designers will do the implementation. And then the verification engineers will come to ensure through the static, formal or dynamic functional methods. Like formal method is like static evaluation check. You provide some train of stimuli like Jasper Gold 2.0. These are the tools by Cadence, LEC Conformal. There are a lot of tools actually which do formal verification. And you will assume some scenario and assert some scenario to check whether the inputs are and the outputs are properly correlated. And you will also see the functions and features claimed in the design are achieved with the power goals or not. Through that, in order to do that, you will do simulation, emulation, and GLS, which is gate level simulations. Emulations is mainly FPGA emulation. So basically FPGA prototyping, and then we run simulations on FPGA. There is emulation. And simulation is basically on the simulator platform based on a compiler. Like we have Synopsys VCS compiler. We have Mentors, right? Different vendors come up with compilers and elaborators library. Now, we will look at different type of cells. For now, let's understand the name of the cells. The names will be very much helpful in explaining what do they do, right? Say, for example, the first one is power switch. You don't have to remember, you don't have to look at these figures also. These are dummy figures. There are power switches and then isolation cell, level shifters, always on buffer, and retention registers, right? We'll go through each one of them now quickly. Now, UPF components. So we'll talk about each components as we mentioned. We need power switches. Now, see this logic. Hope you can see my mouse pointer. I'll give a laser pointer. Okay, so you see a power switch has been implemented at this point, right? What does it mean? If you want to cut off the supply to this blue colored zone, blue colored design module, right? It may have a glue logic inside. It may have some logic inside, but the same supply VDD is being provided to both. Your design may be, have an optimization method in which you may want to, disconnect the device from the power supply, disconnect this module from the power supply. So you may implement a power switch here. Reason is same. Again, I have already spoken about it, to save the leakage power. Because if this is not functional and still it is powered on, there will be leakage current, which will correspond to the leakage power, right? So the UPF command is create power switch. You may not comprehend, may not understand what is meant by this create power switch. I'll show one demo. Through that you can understand. So next is isolation cells. Yeah, next is isolation cells. Now again, very interesting point. If you see in the same circuitry, suppose you power down this, right, using a switch. See, down to the switch, the signal is given as red. That means there is no supply coming to this block, the gray block. I hope you can see my mouse pointer. So this gray box, right, is now powerless. It does not have any power. Can you please tell me what is the value of the signal coming out to the next block? Next block is powered up. If you see, next block is connected through the VDD. That's powered up, right? So what is the value coming up to this? It is X, unprecedented, as I'm telling. If there is no power, you can't guarantee the value. What value will come out from this block? Now, do you want to proceed with that value to the next circuitry? It will go for a toss, right? What we need to do? We now need to isolate this. How will we be able to isolate this? We need to cut off using this isolation cell. If you see this, there is an AND value. Now, using this isolation cell, this isolation select signal, we will cut off based on isolation enable equals to 1. If isolation is 1, there is a bubble logic here which becomes 0. So 0 and with anything will become 0 at the output. So nothing is coming out from this block at least. At least unprecedented X value is now made 0. Made to a value 0. Right? So which will not corrupt the logic in this second block. Interesting fact to see here is, if you see the waveform, you see the ISO signal is going from 0 to 1. The transition is happening before the power down. And of course it is required. After the power down happens to the first block, your signal will already be corrupted. Now doing isolation or not doing isolation will make no sense. I mean, is it justifiable? I mean, are you also acknowledging that it is justifiable? If I have to isolate the signal, if I have to make a disconnection between the second block and first block, I have to do it before I switch off the power of the first block. Otherwise, anyways, the signal is coming from this block, it will be corrupted. So that's the reason before it goes to a power down. Yeah, any question? The bridge? Okay. So we'll move on. So that's the reason before it goes to a power down stage, we are seeing that isolation enable is going high. And once the power is back, you see, the next part is also important. Once the power is back for this block, right? This is the PWR power signal, right? Once the power is back, then we are removing the isolation. Then we are making isolation equals to 0. When isolation is 0, the bubble logic is 1, and with this logic will become this logic, right? Coming from this block. So when the power is successfully retrieved, then we are, removing isolation. Moving on to the next components, which are level shifters. Level shifters I've already mentioned. I don't want to talk more about it, but you'll just look at the command as set level shifter. Now, what is a level shifter in analog perspective? It is just like clamping and clipping, of course. So if you have more voltage from one voltage domain to the other voltage, just clip it, and so that it's a two directional arrow basically. So I don't know, maybe there can be a mistake in this diagram, I can correct it, but it is basically a two-dimensional because the handshake between two power domains are bidirectional. So the level shifter will have to act in both the directions. You see, domain 1 is connected to a voltage supply VDD and VSS is the ground. Domain 2 is connected to again a voltage supply VDD and VSS is ground, but they are connected to different process corners. So it may have different voltages in the different process corners. Now you need a level shifter to just shift up the voltage or shift down the voltage, basically do a step up or step down using a clipping and clamping operation so that your domain 1 and domain 2 are, synchronous in terms of voltage, right? Next is always on buffers. Now, always on buffers are required. They're very much required. You know why? Because in one power management and control unit or in one IP or subsystem, there should be at least one circuitry which is always on. Now, why that is required? If you don't have something always on, you will always require a mechanism to reset the device and then restarting the power, right? If you have something as always on, you can control a lot of things. Say, for example, you can take a backup power from always on. You can, clamp the signals from isolation domain to non-isolation domain. So basically from gated domain to ungated domain. The domain which you're going to gate, the domain which you're going to cut off, from that domain, you can latch the signals to some always on domain, right? Excuse me. So all such things can be done using one always on buffers available in the circuitry, right? The power circuitry. You see the primary power, if the primary power is cut here, you always have a backup power to power them up. So they will never have any undeterministic value at the output. That is guaranteed. Now through that, it helps in a lot of things like it helps in staying the power switches active, retention registers active, speed through paths active, even though there is any active shutdown, right? And again, these things will be clarified when I go on and explain about an implementation. Okay, I'm trying to quickly wrap it up so that I can go to that interesting discussion. Okay, so next is the retention cells. It's again very important feature. So point is when we remove the power, there are certain configurational registers. See, when the system is booted up, BIOS does the system boot up, the basic input output system. And when the system is brought up, there are some configurational registers written by the BIOS. Okay, basic input output system. Now, once that is done, BIOS is nowhere in the picture. Do you anytime see people from computer science background can help us understand? Do they anytime see the BIOS coming up in the picture in the normal operation, in the CPU core operation? BIOS will never come in the picture. BIOS will only come in the boot up time. Now, BIOS is an agent which has done the configurations. It is not the duty of the CPU, firmware, driver, monitors to check what value has been configured, because they don't have a memory. They don't want to invest a memory footprint there. So whenever there is a voltage drop or voltage cut, you're losing all the values. What happens to a register? Register loses all the values. Now who will recover that value? I know there can be a sleep and there can be a wake mechanism, but from sleep to wake, you have lost the memory. Imagine we as human being, we know what is our name, where do we work, what we have to do the next day, if we have to teach or we have to deliver a project or whatever it is. Now we sleep. Next morning we wake up and we don't know anything. We don't know who we are, where are we going, what shall we deliver, what is our objective, what will be our state. Now imagine there is someone to recall, to help us recall who we are. Then again we'll be in the same state, right? Point is, can we have this logic who will help me recall within the design itself in terms of small cells? Yes, those cells are called retention cells. Retention cells usually come with two types of power supply. One, which is the primary supply, and two, which is a retention voltage supply. It's just like one voltage coming from the normal on and off domain, and the other voltage is coming from always on domain. One voltage is VDD, other voltage is always on. The two voltages. Before the VDD is powered off, this part is very important. Before the VDD is powered off, the retention must be high. See, before the power is going down, retention is going high. Once the retention is going high, the voltage supply is by default latched to retention voltage, and the value is locked inside a cell called retention cell. Now, how does a value get locked within one electronic circuit? We know it gets locked in the latches. We have all studied the flip-flops and latches, right? The capture flop and how does it, latch the value. We all have studied. Now, it has a latch inside. It's called a shadow latch. Inside the shadow latch, the value is stored. And after we get the power back, we connect the power rail from V retention to VDD again. So the retention is taken off and we call this event as wake. And the process of storing the value inside a shadow register and retrieving the value from the shadow register are called save and restore. That means saving the value into a shadow register or a shadow latch in a retention cell is called save flow. And similarly, when you restore the value or retrieve the value from the latch onto the register again, back, when you are basically coming out of the retention domain, retention voltage supply, and normal power is restored, we call this event as restore. This is what is written here exactly. What is say, what is restored, we can go through later. Let me quickly talk about the UPF basic commands. So these are the UPF basic commands. See, it is explanatory. If you read, go through, you'll understand how a low power design can be made, can be done. I have taken an example which will immediately start after this, where I'll show step by step how UPF is coded by a designer. Okay, how supply nets are created, right? So far, I mean, this is not of much of interest. I mean, if you want to Google it, such information you can find in Google as well. But what is more important is the concept as why we do what we do, right? So I emphasized more on concept. So I'll talk about the concept part. So you see, there are a lot of commands. These are the TCL commands. I've mentioned the UPF is coded in TCL language, TCL, right? And it is very much available. I guess it's open source. Synopsys TCL format is, again, I believe it's open source for the academia. You can start coding in UPF and integrate that UPF with the RTL, and you can have your own flow. Okay, I'll explain about these commands in the subsequent slides, so I'm not talking about them now. Now the picture over here is a little blurry, but I still prefer to keep it because this is self-explanatory. Now earlier we had non-PA simulation, non-power aware simulation, which would consider only RTL, right? Now we have RTL plus UPF. What a great thing. Now UPF mimics the power behavior of the IP, and RTL mimics the functions and features of the IP. When blended together, it's called power aware design and verification. I hope I'm clear as the topic of discussion today. Once we have that, we basically synthesize them through a tool. A lot of tools like Synopsys DC tool, design constraint synthesis tool, right? So such tools are available to synthesize them into the netlist, and then we have the netlist synthesized separately and UPF synthesized separately. Both of them will just place and route, and then we'll have the placed and routed UPF and placed and routed netlist, which we'll call PD netlist, and we can perform a lot of behavioral, functional, simulation, logical equivalence check and all on every single model. We can do it on the PD netlist. We can do it on the DC netlist. So when it's synthesized, it's called DC netlist. When it's synthesized and placed and routed, it's called PD netlist. Okay, physical design netlist. Okay. Now let's see. As I mentioned, this is the most interesting part of today's discussion. We'll wrap it quickly so that we have some time for the questions and answers. We started a little late, but I'll try to quickly wrap it up. So, understanding UPF implementation. See, look at a UPF file. So there's one file which basically defines what is my subsystem top, how many power domains I have, how many memories do I have in each power domain, do I have a controller or not, power controller or not. So every subsystem must have multiple power domains, may or may not have multiple power domains, but if they have multiple power domains, if they are not single power domain, there must be a power controller. Okay. That is a prerequisite. So one particular logic should be always on domain. When I say always on domain, this particular block in the subsystem should always remain on. The one who controls power flow should always be on, and that should be a bare minimum circuitry. That should not have some lakhs of gates. Okay, millions and billions of gates, right? Then again, my area gate count, right? Then bandwidth product, gate bandwidth product, like whatever is our trade-off, that will happen. That is not required. So this has to be a minimal simplified design module, which will control the power of the entire subsystem, right? Now we'll see how it is actually created. I was telling that I will explain. Don't look at the UPF commands which are mentioned with respect to each element. I will explain each one of them. Now, let us talk about test bench and how we comprehend the design top, duty top in terms of test bench. In test bench, PB, we have an instance of the duty where we connect the ports of the duty, right? and there can be scoreboard also. So you see, TB is the topmost entity which will have an instance of the DUT inside, and DUT ports will be connected to the TB ports, test bench ports, and we drive the stimuli. This is how we do verification. In third semester, I guess, not sure, third or fourth semester, we have something like HDL labs, right? In electronics and communication. So in HDL lab, we do a lot of Verilog and VHDL design verification synthesis. So there, we might have seen these kind of things where we have a test bench and then we have a subsystem top, right? So in test bench, we instantiate the subsystem. In subsystems, there are power domains instantiated. So now, how will I tell through a UPF coding that this is my top? So this is the command to use it. Set design top, and then TB slash subsystem. That means inside the TB, whatever subsystem is instantiated, that is my design top. Okay, so I'm just saying set design top. That is the command. Okay. Now, next point is set scope. When I say set scope, that means this has how many scopes? I'm specifying the scopes. Okay. So I'm just mentioning how many scopes does it have. It has currently 3 scopes, right? So one is this P1, other one is P2, and it has got a power control. A power control is not a scope of this. Then you see this, the first scope is P1, and P1 has M1 and M2. P2 also has M1 and M2, right? So this is the way we just mentioned. We just elaborate the design as how many things are, how many memories, how many modules, how many processors are there in one subsystem, right? So all these are elaborated using set scope. Now is the complicated things starting, like defining the power domain. Now, you see, this is what we already have. This is my design, entire design. This is my design top. It has 3 modules. One is P1, other one is P2, other one is power control. And then P1 has a module called M1 and M2. Similarly, P2 also has a module called M1 and M2. How do I define the power strategy? First, I am doing set scope sub. That means I am setting the scope as sub. Everything will be with respect to the subsystem, which is the DUT top. Now we are creating the power domain. You see the command which is used, create power domain, PD sub, that we are using, creating a power domain, that PD sub, right? Now you see PD sub is including a scope. So it's mentioning include scope. What is the scope that is included here? The scope is nothing but power control. If you see here, right? The power control is a scope. So the first domain sub is in a big domain, which is PD sub. So PD sub is the power domain for the subsystem top, which is the DUT top. And now we are creating individual power domains for these blocks. If you see, we're creating one power domain for this block and another power domain for this block. For one P1, M1, M2, there is one block, and P2, M1, M2, there is another block. Now, there are 2 domains specified here, create power domain PD proc 1, that's for P1, M1, M2, and PD proc 2, which is for P2, M1, M2. Now, within P1 and P2, for M1 and M2, I am defining one more power domain. Now, what are the, what is the fun in it? Why am I creating so many power domains? You see, again, another power domain is created. We are mentioning the elements which are covered in that power domain. If you see here, create power domain, PD proc 1. In this power domain, what is covered? Only element P1 is covered, right? Again, mentioning PD proc 2, right? Create power domain PD proc 2. What is the element covered there? Only P2, nothing else, right? Then again, we are creating another power domain, PD proc to mem, right? Processor to mem. How many elements are there? I am mentioning P2's M1 and P2's M2, 2 modules. Why are we creating so many power domains? Again, we'll go to the root of this discussion where we started today. We want to switch off M1 and M2 of P1 and P2 processors. We want to switch off individually the memories of 2 processors. Sometimes we may want to switch off complete P2. Sometimes we may want to switch off complete P1. If I switch off complete P1, I will be able to switch off M1 and M2 also. If I switch off complete P2, I'll be able to switch off M1 and M2 of P2 also. If I want to keep them alive, I can keep them alive using this voltage and remove this voltage, right? So there are a lot of customization possible based on my voltage management, which memory I may require, which memory I may not require, which processor is of my often use, which processor is only used for error reporting. Whenever there is error, that will be reporting. That time I'll wake it up, right? So that's the reason I'm creating so many power domains. The power domains can be created in multiple ways. Now, if you have understood how power domains can be created, these are few more examples of power domain creations. We are setting a scope as sub, and inside that sub, you see there are a lot of subscopes created. So here we are mentioning first, create power domain PD sub, which includes only the scope, which is scope is sub, and create power domain PD proc. Now in PD proc, you see there are two elements. Elements are P1 and P2, right? You see elements are P1 and P2. And again, we're creating another power domain, which is PD mem. In PD mem, we are seeing P1 by M1, P1 by M2, P1 by M1 and P2 by M1 and P2 by M2. These are the elements, right? So we are just listing the elements here. You can see, right? This is the way we are partitioning. So this is a voltage partitioning done in a different way. Now we are done with the voltage partitioning. Now we need to supply voltage. For supplying voltage, we need two things. If you can see my screen, we need two things. One, we need a port. We need a port, right? These ports are nothing but the plugs, right? Sockets, which can be connected to plugs. Plugs are nothing but the voltage supplies in the test bench or in the real silicon, right? So these are the ports. And then these are the nets. Whatever you see here, these are the nets. Okay. So now we need to create supply ports and supply net. We are mentioning here create supply port VDD, which will create the port here. This is the VDD port. We are saying create supply port VSS, and both are direction inputs. That means both are receiving voltages input, right? These are not voltage generating. These are voltage sink. These are not sources. These are the sinks. Okay. Now create supply net. Here is very important. The name of the supply net, I am calling it as power. The domain is PD sub. That means whatever you connect from VDD, you are connecting to sub, which is PD sub. Whatever is connected in PD sub, that will be in the same voltage. And I'm naming that net as power. That means it's just a wire connection from VDD to the power control, the power domain controller and the sub, which is duty top. It's the same power being floating through it. The ground and VDD are now connected to the top. Okay. Similarly, we can have, power supply net. Again, the name is power. Ports are VDD and ports ground, right? And those can be connected to different domains like primary power net and secondary power net, right? Power ports. All these can be specified. Right? Here, there is a usage where we are saying that once the supply net is created, whose name is power, you can reuse that supply net. Basically, you can tap from here and you can connect to the next power domain if you wish to. Then the point is, if the power is gone, say for example, if the power is gone at this point, if the power is cut, if the VDD is cut, it will not be able to feed this block also. It will not be able to feed this block also. Right? So create supply net reuse is in a way helpful because you can supply the same voltage to both the domains. But ideally that is not the intention. So you should not be doing it. And set domain supply net is basically, connecting the same net to the supply port of the next power domain. This is an interesting thing. So basically you have a power switch implemented. We already have spoken about power switch. So this is the way to create a power switch. You see the option mentioned here, the create power switch. The create power switch will create a power switch, and through that power switch you can control whether you want to allow or disallow the power to flow through this or not to the next block. In case of the same supply net reuse, we can use a power switch to control the optimization, control the voltage supply to the next set. Okay. And create supply port, we've already mentioned. Create supply net, reused, already mentioned. These are just examples of them. Now add port straight. This is important. So every port is having a certain voltage state, right? Either 1.0 volt or 0.8 volt. The kind of discussions which we were having in the beginning, that CPU may need some operating voltage, camera or some other block, right? GPIO may need some other operating voltage, right? So all these voltage levels are defined here in the power state. And corresponding to that, we have the power state table. So if you see here, this is how the power state table is mentioned, where all the voltage levels are listed, and in all kinds of operation, in the normal mode, sleep mode, and hibernate mode, what should be their standard values that they can be comprehended, whether they're off, totally off, or scaled down, or whatever their voltage values are, everything can be mentioned here. So PST is nothing but the power state table. So this is called power state table, that can be written in UPF, that in what kind of stage, how do you want to scale down the power of the sir. Now set retention and set retention control, these are the two options. You can see there are retention cells. It's shown like this is the symbol of the retention cell here. So you see there are two retention cells here, and one here and one here. Before going to power down, because you see the supply nets for both VDD and VSS, these are basically disconnected through a power switch. So before going to a power down state, you can basically disconnect them, and you can set retention, and you can store the values so that the BIOS doesn't need to come back to restore them. Similarly, if you see isolation, so these are the blocks we are isolating, because we have a power switch here. The signals from P2 and P1 to sub may conflict, sub may be corrupted, right? Subsystem may be corrupted. So you have one isolation cell here and another isolation cell here. And this is the command to set the isolation. And you can mention the domain, and you can mention applies to outputs or inputs, right? And you can also mention the strategy, the power state table is following, right? Another isolation strategy is again mentioned here. It has got a lot of dependents like VDD and VDD2. Similarly, we have level shifter implementations. You see level shifters are implemented at different stages, where we have two different voltage levels, but signals crossing from one domain to the other. So you might need a level shifter. So it's just a command. With one command, you can invoke the standard library and you can have the level shifter implemented. So yeah, so this was all about my presentation. Tried to cover. It's basically a long thing. I mean, it requires at least 2-3 days session to complete the low power design basics. But I tried to complete in whatever manner it might be effective, or it will give you an abrupt idea and get started on the UPF. Hope it will help. Feel free to share any feedback, and I would look forward to any questions you might have at this stage. And if not, we can wrap up the session.
Thank you, sir. It was a very interesting and informative session. Dear participants, we have, if you have any kind of queries that you would like to ask our resource person, we are open. The session is now open for the questions. In case of any clarity that you want, definitely you can ask these questions.
Yeah, so I would just like to clarify one more thing. So in the backup slide, I've just kept one more thing. Like this is a real design module of the Synapse Techno India. This Synapse, basically, you might have heard that we have all these Boeing aircrafts, right? So for Boeing aircrafts, Synapse design, does a lot of manufacturing. And then this is a real example. One of my friends has done it. It's created one UPF on voltage supply. This is an example. You can zoom in and see. So all the examples of level shifters, power switches, everything is explained here. It's a real industry application. You can refer to that for your understanding.
It is our distinct pleasure to express our sincerest gratitude to Mr. Surjit Bhattacharjee for his erudite and captivating presentation. His profound expertise and insightful commentary have significantly enriched our understanding of the subject matter, and we are deeply appreciative of the time he has taken to share his knowledge. We do admit that because of the time constraint, You wanted to give more of the information, but you could not. But still, we do appreciate the time that you have taken to share your knowledge with us, sir. Thank you, Mr. Sujit Bhattacharya, for your valuable information and your time. Thank you, sir.
Thank you so much. Thank you. Thank you for inviting me and having me, with you all and sharing our presentation. Thank you.